Hey everyone, so this is going to be I hope a all-in-one sorting video where we're going to talk about insertion sort, quick sort, heap sort, radix sort, tree sort, and merge sort. So I'm going to try and do it kind of quick. Let's see how it works out. So first, starting off with insertion sort. This is kind of the most basic of all of these sorting. All you really do is you kind of you move your list up. So you start at the left element here, and you make kind of an individual list like this. So you say, okay, well, is my little list here, is this in order? Well, it only has one element, so it has to be in order, so of course it is. So that's the first one. So then we move our little line up. Now we have a bit of a bigger list. And so we say, okay, well, is this list in order? Well, this element's okay, but is this element okay? You take the 2 and you compare it to the last element. So we're comparing 2 with 3. 2 should be going before 3. So now you're going to swap both numbers. So you swap them, and then we end up with 2, 3, 7, and 6. So our line's moved up here. So now we're comparing 7 with 3. 7's greater than 3, so we're good. And now, finally, our line moves up a little bit to include all of our numbers. So now we're comparing 6 with 7. 7 is greater than 6, but is in the wrong place, so we swap the 2 numbers. So then our new list is 2, 3, 6, 7. We're all good now. That's insertion sort. Quick sort is stupid and complicated, but it's one of the best sorting algorithms we've got, so we gotta learn it. So let's picture our list as having kind of 3 sections. This middle section is going to be your pivot number. This is one number. This section is going to be smaller than your pivot. And naturally, this section is going to be larger than your pivot. My tablet's acting up, sorry about that. So for our pivot, we're going to pick 7 because it's right in the middle. And you want to pick a number that is as close to the middle as possible. So now we're going to start in from the left. And now we're looking at 9. 9 right away we can tell is supposed to be on the other side. It's bigger than 7, so it should not be on this side. It should be on the other side of 7. So now that we have a number from our left side, we have to find a number on the right that we can swap it with. So 10 is okay. 10 can stay there, but 6 rather cannot, because it's smaller than 7, so it has to go on the other side. So now we can swap the 2. So this will be our new list. I'm just going to cut out for a sec. Okay, so this is our new list. Notice that we have 6 on this side now and 9 on this side. This list is still not ordered though. You just swap the 2 numbers, right? So now what we have to do is we have to chop up this list. Quicksort is a divide and conquer algorithm. So if you're doing it in a program, you'll take this side and you'll recursively repeat quicksort. So with our eyes, we can tell that 8, 9, and 10 is already sorted, but a program won't know that off the top of its head, so it'll have to go through quicksort again here. But 6, 2, 3 we can do ourselves because we know that's not sorted. So our new sort of mini list is 6, 2, 3. Our pivot will be 2. Really only because it's in the middle. And now we're going to look at the right side. So right away, or left side, right away we can tell that 6 should not be there. It should be on the other side. So now we're switching to the right side, and right away we can tell that 3 is perfectly fine. So that means that 6 doesn't get swapped with anything, but it gets pushed to the other side of 2. So that means that our new mini list will be 2, which is our pivot, and then 3, and then 6, because 6 got added on to the other side. So now this list is sorted. Our other list is already sorted. So then we end up with our sorted list. So if you were to look at this in terms of a tree, you can see the divide and conquer in action. So you'll start out with a list of n elements, and then your next 2 mini lists will be divided in half. And then if you have a long enough list, those 2 will get divided in half again. Okay, so that's it for quick sort. So heap sort is one of my favorite sorting algorithms because its concept is super easy as long as you understand what heaps are. So one of the best ways to do heap sort is using a min to max heap. Sorry, this is a really bad representation of a heap, but basically the smaller number will be at the top and the larger numbers will be on the bottom. And that is because what you do with heap sort is you toss all of your data into a heap. So let's say you have 3, 2, 8, 7, 9, or whatever. You toss all of that into a heap. So I'll cut out for a sec. So this would be an example of our heap with our data. And the way heap sort works is we just cut out the root, toss it into an array, and then we do our heap thing where we promote the rightmost child of the bottom level, which would turn our heap into 9, 3, 8, 7. Oops, we used 9 already. So that's our new heap. And obviously this doesn't work for a min heap because 9 is not our smallest number. So this will have to be reheapified. Okay, and so 3 will be on top, followed by, if we're bubbling, then you'd move 9 down to here. But we're going to skip a couple steps. 7 will go here because you're bubbling once again, because 7 is smaller than 9. And then 8 can stay in that its little spot there. So now you really just repeat. Now you take the 3 off, you promote the rightmost child. So 9 takes its spot as king again. We have 7 and 8. Again, this is no good. So that will turn into 7, 8, 9. And then again, you keep repeating, but every single time that you delete your root, you add it to your array. So we have 2, and then we deleted 3, and then we'll be deleting 7 here. So you notice that the pattern is in order. So 2 is our smallest, then it's 3, then it's 7, and then if we kept going, we'd end up with 8 and 9 at the end of our array. So now we have a sorted array. You can also do heap sort inside an array without ever needing a heap object or a heap structure. And the way you do that is any node in your array or cell in your array at index I, as denoted by this arrow, has children at a 2 times the index and at a 2 times the index plus 1. So that's if you're doing it in code. This gets kind of confusing though, so if you're doing it on paper and you're a visual person like I am, I would recommend just doing the heap. So that's heap sort. Radix sort is a little bit strange because it never actually does any comparisons. It's called an address-based sort, which is a type of sorting algorithm that does exactly that. It doesn't do comparisons. So we want to draw buckets where our numbers will go. I'm going to cut out for a sec and draw all these. Okay, so I took the liberty of also writing down our list of numbers to compare. So now what we're doing is we're just looking at the last number in each one of our list numbers here. So we have 4, we have 7, we have 3, we have 0, and we have 3. So in order, we're just going to toss them in the bucket. So we have 964 first. So 964 is the first in the 4 bucket. And 097 is the first in the 7 bucket. 123 is the first in the 3 bucket. And 870 is the first in the 0 bucket. And then 913 is the second in the 3 bucket. So now what we do is we go in order from the 0 bucket onward, moving from the bottom of the bucket to the top to make a new list. So our new list here will be 870, and then 1, 2, 3, and then 913, and then 964. My 4s keep messing up. It's kind of annoying. And then 097. So now we're going to look at the middle number. So I'm going to cut out for a second, redo these buckets. Okay, so this is what our buckets now look like for the middle number. As you can see, the order is getting kind of screwed up here, but we'll see that in the final round of sorting that they will be in order. So now our new list, again moving from left to right and going from bottom to top, is 913, 123, 964, 870, and 097. So again, now we're looking at the final digit, the first digit. I'll cut out and redo the buckets. Okay, so now we'll have our final sorted list. And Radix sort has magically sorted everything perfectly, with 097 being our first, 123 being our second, 870 as our third, 913 as our fourth, 964 as our final. So that's Radix sort. Let's move on to tree sort. Okay, tree sort. So let's say we have a list 3, 7, 5, 9, 12, 1. You essentially want to take some middle value of your list and turn that into your root. So I'm going to cut out and I'll make the tree and come back, just because I may screw up a couple times doing this. So I'll explain it when I come back. Okay, so the idea here is you want to pick, again, just like a middle value. So I picked 7. I felt like that was a good kind of middle value. And then on the left, you see whatever values are smaller than 7. So we have 1, 3, and 5 here. I could have maybe put 5 here instead, but then our rules would have been broken, because then I would have had 3 on the right there, which doesn't work. So you're able to switch that around. You make that 3. So 5 is still greater than 3 but smaller than 7, and 1 is smaller than all of those. So it's the same thing on the right here. Our lowest level, this is still a complete binary search tree because everything's pushed to the left on the lowest level. 12 is bigger than 7, 9 is between 7 and 12, so this is all good. So now that the way you find your ordered list is by an in-order traversal of your tree, so just recall that that is left, root, right. So let's do that right now. We start from the top. We have to go all the way left to visit 1, and since we've gone left, now we can go to our root, which is 3. And now that we've gone to our root, we can go right, which is 5. And since this entire side is left of our main root, the 7, now we can go up to our main root and now we visit its right branch. Now we've hit another root, so now we have to go left, and then we can go back up and visit the root. It doesn't have a right child, so we're okay with that. So let's write down our list. So let's look at our first step. Our first step was 1, and then we moved up to 3, then we moved back down to 5, and we scooted up to 7, and then we went past 12 because it's a root. We went to 9, and then finally we revisited 12. So that's your sorted list, and that is tree sort. Alright, so this is going to be our merge sort list. And merge sort, you just divide your list in 2 until you end up with the shortest list you can get. So we have 6 elements, so we want to end up with 2 lists of 3, which means that we're going to end up with 1 list of 2, a list of 1, and then the same on this side, a list of 2, and a list of 1. So that means that we have 4 and 9, and once you end up with your small lists, you sort those, and then you just remerge after. So 4 and 9 are good. Those are sorted. 8 is only list of 1, so it's good. It's sorted. And then we have 1 and 3. Turns out that that's good. It's sorted. And then we have 6. Oops. Turns out that's also good and sorted. So now we merge everything back together. 4, 9, 8. I may have picked a bad list. This is going to seem a little bit redundant. But oh well. So then we merge this again. 1, 3, 6. So in this list here, we notice that it's not in order. So if you're doing this in code, you would have compared everything once you're remerged. So you would end up with 4, 8, and 9. This list, on the other hand, is okay. Then we merge again, compare again. So we'll end up with 1, 3, 4, and then 6, 8, and 9. So the essential bare basics behind this is that you're chopping it up as far as you can go, sorting up those little bits, and then putting it all back together, sorting as you go again. So yeah, that's it for those sorting things. I'm just going to include some general information about timing and complexity and stuff, but if you're not interested in that, that's essentially the end of the video for you. Alright, we're going to talk about stability. So stability is when list entries that are pretty similar still have their order maintained. So a good example is if something like Amazon or whatever was taking orders and they sorted their orders by province. You'd have like Ontario, and then like Alberta, and then Quebec, etc. And there's different times for these orders. So let's say this one was done at 3:20, and this one was done at 2:10. If you're sorting by province with an unstable algorithm, your time won't be maintained. So then when you're going through the orders, you're going to be completing this one done at 3:20 before the one that was done actually before it, before the one that was made before it. That's not really fair. So a stable algorithm, you could say, keeps perfect order even when you have similar list entries. So some of the stable algorithms that we talked about are insertion sort, Radix sort, and merge sort. So those guys are all stable. Unstable ones are quick sort and heap sort, mainly just because you're dealing with that one value to shift everything around, and there's not really room for 2 values. So then what is the best algorithm? They're each good kind of in their own respects. Quick sort is a crowd favorite. But the thing is that it uses recursion, which is bad for stack space. If your list is already mostly in order, then insertion actually tends to be okay, despite its best case being O of n. So when your list is already mostly in order. Okay, and then again, if you're looking for stability, if you're dealing with pretty sensitive data, you want a stable algorithm, which would mean that the best one is merge sort. Okay, that's finally the end of the video. I have a headache now. I'm starting to lose my voice. So I apologize if the last bit was kind of stupid. But all the sorting explanations I feel were okay and on point. So thanks for watching. Subscribe if you want. Ask questions in the comments. Suggest ideas for new videos, etc. You guys know the drill. Happy studying.